Sorry, guys. It's not going to be the top.
Okay, so we saw the three simple tissues, squamous, cuboidal, columnar. Takes us to the stratified tissues. So as far as the pictures go, we only have two stratified tissues, as you know. We have stratified squamous, and it comes in two varieties, keratinized and non-keratinized. You know that there is another stratified tissue. Some people call it stratified cuboidal, some people call it stratified columnar, some people say it's the same thing. I'm going to call it this, you can call it that. Other people say, no, they're stratified cuboidal and they're stratified, but I don't care. Okay, it's not worth arguing about. We don't have a good picture of it anyway, as you know. So, for us, the stratified tissues amount to the two varieties of stratified squamous, keratinized and non-keratinized. Now, what does keratin do to the keratinized stratified squamous that makes it different from the non-keratinized stratified squamous? Dries it out. Yeah, keratin is a protein that dehydrates the cells, the tissue, dries it out. So we'll start with the keratinized variety. This is a great example of using low magnification and identifying the organ, and so everybody recognizes this as skin, and when you say, oh, that's skin, everything you know about the skin starts racing through your mind, and you're preparing for whatever question I might ask. Of course, this is the epidermis of the skin, the keratinized stratified squamous. This is the dermis, dense, irregular. If we start increasing the magnification a little bit, things become a little clearer. Because the epidermis, which runs from here all the way to the surface, and you can follow along here and see where the epidermis and dermis come together like interlocking fingers. I think I used the word the interface. That's simply the junction between the epidermis and the dermis. Doesn't matter if the deeper cells are cuboidal. We choose the shape based on what's on the surface. And so when we get to the surface, the cells are flat, they're dead, they're keratinized, they're just falling off on the floor every time you wash yourself. So it's a very thick, very protective layer. The deeper part of the skin, the dense irregular, of course, constitutes the dermis. Now, if we compare the keratinized stratified squamous to the non-keratinized, the difference is pretty obvious. It'll be more obvious when I blow it up a little more, but in this case, the epithelial tissue is right here. This is pretty much just like the dermis of the skin, the connective tissue that's under the epithelial tissue. But when we look at the non-keratinized variety, the big difference we see is that all of the cells are nucleated, so that there are no dead cells sloughing off. Those cells will slough off, but they're living. So the keratinized and non-keratinized are all about protection against abrasion, things like that, a thick protective layer, but the keratinized is to be dry, the non-keratinized is to maintain moisture. Let's go back to the low power of the skin, because just as we did on Wednesday, there are several points I try to make when we look at these things and preparing you for the practical. On Wednesday, one of the points I made was the difference between an organ and a structure. So in other words, we looked at perhaps this. Name this organ. You said lung. Name this structure. You say, what are the functional units within the kidney? So those are structures. Okay, well along those lines, let's do that same sort of thing with the skin. So name this organ.
Integumentary system.
No, it's not. An integumentary system is not an organ, is it? It's a system. Now, if you wanted to call it the integument, that'd be great. That'd be great. But I'll take skin. Name this part of this organ. Epidermis. Okay? So the stuff is not difficult. You just want to make sure you're listening and you hear the question and you answer specifically. Give me 3 locations of this tissue. What? Esophagus? You said throat? Okay. Esophagus, throat?
Lining of the oral and nasal cavity.
The lining, okay. You said nasal cavity, you said lining of the oral cavity. That's kind of like throat or mouth. Okay, good. All right, our next 2 are the very specialized tissues. The specialization being the cilia. And I may or may not, I honestly don't remember, you can tell me if I do, on the DVD mention that some of the slides of the trachea show the esophagus as well, because it's a slide where they simply cut the head off the mouse. Do I mention that? And take a very thin section through the neck. You can pick out the trachea versus the esophagus because the trachea doesn't collapse. You know why it doesn't collapse. The cartilaginous rings. So this is the trachea, this is the esophagus. So again, low power, getting your bearings. If you know that this is the trachea, well, pretty much everything you know about those 2 tissues is right there on the tip of your tongue, whether I were to ask you about the pseudostratified ciliated columnar epithelial tissue, or whether I were to ask you about the hyaline cartilage. Please don't answer with PSCCE, okay? You can use ET and CT to abbreviate things, but with the pseudostratified ciliated columnar epithelial tissue, you need to write it out. It's kind of like DNA or ATP. The very first time, you gotta say the word, spell the word, write it out, whatever, and after that, everybody calls it ATP or DNA. But so this PSCCE needs to be written out during the practical. So blowing things up just a little bit, we see the hyaline cartilage, we see the PSCCE, and is this the one where on the video I just get so sick of saying pseudostratified just ad nausea? And there we can actually make out the cilia fairly clearly. They're a lot clearer on your computer than they are right here. This thing never seems to be perfectly in focus. What are the 3 types of cells found in this tissue? Goblet cells, basal cells, and the ciliated columnar cells. Now I know what the goblet cells do because we talked about those in the context of, probably simple columnar on Wednesday. What do the basal cells do? The basal cells are the mitotically active cells. So the basal cells are undergoing mitosis to produce new cells. Now, all of this working together, it's really pretty simple. The goblet cells are secreting mucin, mixing with water, forming mucus. The mucus layer is here on the free surface of the tissue, and particulate matter gets trapped in that sticky mucus layer, and the moving cilia are bringing that mucus layer up to your throat. That's why you constantly have to swallow. Maybe if you're hiking, you might spit, but when you're inside, I trust you don't just spit in the floor. But you always are bringing mucus up to your throat, and you're swallowing it. And what that comes from, the respiratory tract. You're cleaning the respiratory tract. If you've ever wondered why smoking makes people cough, it's because smoking paralyzes the cilia. So you have to cough to bring the debris up from the lungs. The paralysis, by the way, is temporary, so the cough will generally go away. Now, I don't know if it goes away if, somebody's 80 years old and they've been smoking for 75 years, but it may become permanent at that point. Another point to be made with the slide of the trachea, and I don't know why I changed pictures. These are really the same. They're just oriented differently. But it's a good example of levels of organization. So cells form tissues, tissues form organs. An organ has to be made of at least two different types of tissue. But we use the trachea in this context, epithelial tissue, the PSCCE, and then we get to the connective tissues. And after the bone, you have the three types of cartilage. You come back and look at the trachea again to focus on the hyaline cartilage. This is just another slide of the trachea. I like this one because it shows why people think this tissue is stratified. I mean, you truly see nuclei at different heights, which would lead you to believe that you have cells stacked on top of each other, but you don't. It looks like that because of the three types of cells. The basal cells have their nuclei down very low, close to the basement membrane. And then the goblet cells and the ciliated columnar cells are above that. So you get this appearance of stratification, and it's a great example of how we really only know what we know because of people looking at things magnified tens of thousands or hundreds of thousands of times with the electron microscope. The other ciliated tissue is another one that requires a brief, not as detailed as anything we did last week, but a brief turn on the lights and draw a picture. So this is a very low magnification of a cross section through the fallopian tube, also called the uterine tube, also called the oviduct. Humans, it's most commonly called the fallopian tube. It is convoluted, and those convolutions do increase the surface area, but they're also very important to trapping gametes. Now, if you compare these convolutions to the convolutions of, say, the small intestine, there's no way that you would get one confused with the other. Look at how ordered and regular the convolutions are in the small intestine. And in the fallopian tube, the convolutions are just sort of crazy. Increase the magnification here gradually. And you finally get zoomed in on it. And you can actually detect, I'll say, the cilia on the free surface. They're not as obvious as they were in the trachea, but you definitely can tell that the surface is not smooth. And that less than smooth appearance is because of the cilia. So what the ciliated or simple ciliated columnar epithelial tissue is all about in the fallopian tube, just making sure there wasn't another picture I wanted to look at, is trapping and moving gametes and the embryo. So this is a coronal female, just parts of the reproductive tract. Tubes, the uterus, the cervix, vagina, ovaries. So there's no actual physical connection between the fallopian tubes and the ovaries. There, if we blow that up, there's literally a space between the fallopian tubes and the ovary. The fallopian tubes have these little finger-like projections called fimbriae, and they're moving like this, creating sort of almost a suction, so that when ovulation occurs, the egg is encouraged to move into the fallopian tube. Fertilization actually occurs way out in the fallopian tube. Fertilization does not occur in the uterus, okay? It occurs in the fallopian tube. So the egg has to travel that far. The sperm, which are deposited at the cervix, have to travel that far. Then, of course, you have your two haploid cells creating the diploid embryo. The one-cell embryo is called a zygote. And that embryo now has to travel from the site of fertilization back to the uterus to implant. As that embryo is traveling from the site of fertilization back to the uterus, division is occurring. So we go from 1 cell to 2 to 4, 8, 16, 32, and typically about a 64-cell embryo by the time the embryo arrives in the uterus and implantation occurs. So these cilia are facilitating this movement of the gametes, of the embryo. The cilia are helping to trap things so that we don't have things going on out here. You've all heard of an ectopic pregnancy. An ectopic pregnancy can be a tubal pregnancy where implantation occurs in the fallopian tube, but there's really nothing to guarantee that the egg doesn't go out here somewhere into the peritoneal cavity, and the sperm could go out there too, and we can have a true ectopic pregnancy, but beyond just a tubal pregnancy. We don't really understand how the sperm travels that far. We assume that the cilia help. We also know, though, that prostaglandins stimulate contractions in smooth muscle tissue. You learned that last week, I guess. We know that smooth muscle tissues, the muscle tissue in the walls of hollow organs. So we assume, and here, think about science. Who are you going to ask? There's no owner's manual. We assume that prostaglandins, because they're found in semen, might be important in stimulating contractions in the fallopian tubes to facilitate the movement of gametes and or the embryo. That assumption is basically validated by the fact that you have men who are non-sterile but infertile. If you're sterile, you don't make sperm. If you're infertile, you just can't impregnate a woman. So you can be infertile, but not sterile. In other words, you can make sperm, but can't get a woman pregnant. You can have a normal, healthy sperm count. And so sometimes you see men who are non-sterile, but they're infertile, and when you analyze their semen, you'll find the prostaglandins are missing. Of course, that's, how science works. You figure stuff out, put it together. Okay, our next one is glandular epithelial tissue. Now, in a histology class, at this point, we would cover every gland in the body. That's why a histology class would take an entire semester versus it just takes maybe a week in this room, 2 weeks in the lab, and 40 or 50 hours of you working at home, or however long, I'm sure you can tell me. But two glands that we have in the context of glandular epithelial tissue are the thyroid gland and the pancreas. Now, the thyroid gland, of course, has a specific epithelial classification, simple cuboidal epithelial tissue. Some glands have that, other glands don't. The pancreas is one that doesn't have that. But I like the pancreas because it belongs to two different systems. The digestive system, you have the acinar cells making the digestive enzymes that travel through the pancreatic duct. You have the islets of Langerhans with the alpha and beta cells making the glucagon and the insulin and the whole blood sugar homeostasis. Okay, I'm not going to rehash that with you. You've got that in your notes, don't you? Your books, because I gave it to you. It's in the documents that you have. So, for example, you'll see some of it here. I believe this is the lecture notes. It could be the supplement. I don't know. Doesn't really matter. And then in the other document, I talk a little, give you sort of, these are the notes. The other one must have been the supplement. Give you sort of an outline for homeostasis. So what I want to do at this point is talk about homeostasis beyond the information that you have already extracted from the notes, the supplement, chapter 1 of the book, and the DVD. The word is misleading because stasis, of course, is where the word static comes from, stationary. And so you would think it means not changing. Well, it doesn't really mean that. Now, well, I guess occasionally it does, but more times than not, it doesn't. An example of where homeostasis means stationary would be your body temperature. Your body temperature is 38 degrees Celsius, 98.6 if there are any silly Americans in the room. But whether you're outside in the winter time, I don't care if it's 20 degrees or negative 20 degrees, your body temperature is 38 degrees. If you're outside in the summertime, I don't care whether it's 80 degrees or 110 degrees, your body temperature is 38 degrees. So that is an example of homeostasis. It's also an example of what you would think the word means, stationary. But more times than not, homeostasis means that changes occur inside the body to meet whatever's changing outside or whatever the body is doing from this to that. So for example, you're all sitting. Your heart rate right now, just call it X. Okay, get up and run toward the door. Don't really. But what would your heart rate do? It would go up. It would accelerate. Why? To deliver more oxygen-carrying blood to the muscles that you're using to run with. You would also breathe more rapidly. You would breathe deeper. That's homeostasis. That's all it is. There are millions and millions of examples of homeostasis. Back to the temperature thing, though, because there's a true story 100 years ago, maybe 150 now, because I probably started telling the story 50 years ago. But they put a man, a dog, and a steak in a room that was heated to some ungodly temperature, and I don't remember. It was, we played checkers that day. Do you recall the temperature of the room?
Yes, I do.
Was it 150 or was it 180?
180.
Okay. It may have been 200 degrees. It was an ungodly temperature. But they put a man, a dog, and a steak in this room and heated it to, well, he remembers 180 degrees. And they left him in there for 30 minutes. Maybe it was an hour, I don't know. But they opened the door, and the man and the dog, the steak was cooked. What's steak? It's muscle. We generally don't eat muscle off people unless, we're stranded in the Alps and that's all we have. But we eat muscle off of any other animal, deer, elk, fish, cow, pig, chicken. So why did this steak cook? Well, it was the dead piece of meat. It didn't have the ability to regulate its body temperature, so the temperature went up. The blood sugar, of course, is a great example of homeostasis with the islets of Langerhans, insulin, glucagon, and all of that. That, of course, ties in specifically with your G words. You have a list of hormones that go with glycogenolysis, gluconeogenesis, et cetera, et cetera. So what I want to look at is bone homeostasis. And you've seen this in your lecture notes under the context of homeostasis right here. And I think you've probably also seen it in the supplement, but maybe not. Yeah. So you don't see it in the supplement.
Is it the bottom of the supplement? Or
It-
is that?
Well, one place where it might be mentioned in the supplement is in the context of simple cuboidal, because some of the hormones come from the thyroid gland, and so you do see thyroxine, calcitonin, parathyroid. So it is in the supplement as well. So you guys are more familiar with these notes and all than I am, because you use them every day. I generally don't ever look at them. One of the TAs will say, "I updated your notes," and I'm like, "Oh." All right, bone physiology. So we've got two types of bone cells. And the other thing mentally to be doing here is tie all of this in with cholesterol. Cholesterol forms steroids, estrogen, testosterone, low body fat, pathological fractures, not stimulating your bones. So you have a ton of stuff that we've already discussed that you can tie in here. So the osteoblast, of course, increase the bone calcium. And of course, we could also call that increasing density or increasing mass. And they take the calcium out of the blood, so the blood calcium goes down. And of course, because I've told you that calcium is to bone as glucose is to glycogen. Again, lots and lots of things we've already discussed to tie in here. The osteoblast are stimulated by estrogen, testosterone, growth hormone, and thyroxine. You already have that in your notes as well. What we haven't discussed, the new material here, is to talk about the osteoclast. Now, you know that they take the calcium out of the bone, so the bone calcium goes down. You know they deposit the calcium in the blood, so the blood calcium goes up. But it's the hormones that act right here that we have not discussed. We have two of them. We've got, the first one is called parathyroid hormone. Let me just give you a little footnote over here, because that got kind of small. Goes by two other names. Parathormone and PTH. So parathyroid hormone, parathormone, and PTH, they are the same thing. The other hormone that acts on the class, and what parathyroid hormone does, it stimulates the osteoclast. The other one is called calcitonin, and it inhibits the osteoclast. So let's think about those two hormones. if parathyroid hormone stimulates the osteoclast, and the osteoclast are the cells that take the calcium out of the bone, what's going to happen to bone mass when parathyroid hormone is active? Get a decrease in bone mass. And where does the calcium go? So you get an increase in blood calcium. Now, calcitonin, the other hormone here, inhibits the osteoclast. I'm going to try to trick you, okay? I'm being upfront with you. I'm going to try to trick you right now, right this second. Your goal is to not be tricked. So parathyroid hormone stimulates the osteoclast, calcitonin inhibits the osteoclast. Therefore, these two hormones do the opposite thing to the osteoclast. True or false?
False.
True.
True.
One stimulates the clast, one inhibits the clast. They do the opposite thing to the osteoclast. Okay, I haven't tried to trick you yet. I'm headed that way. It's coming in a second or two. We've established that the two hormones do the opposite thing to the clast. This one stimulates the clast, this one inhibits the clast. Because they do the opposite things to the clast, it would infer that they must do the opposite things to bone mass. So since this one decreases bone mass, this one must increase bone mass. True or false?
False.
False. False. So it sounds like I didn't trick you. Why, if they do the opposite thing to the clast, stimulate the clast, inhibit the clast, why don't we have the opposite effect on bone mass? All this does is we stop taking calcium out. If we stop taking calcium out, that doesn't increase the mass, does it? We just stop decreasing the mass. It's exactly like money. If you put money into the box, the amount of money in the box goes up. If you take money out of the box, the amount of money in the box goes down. Well, if you stop putting money in, or you stop taking money out, the other doesn't happen. I mean, if you stop taking money out of the bank, does the balance go up? No, it just stops falling. Don't tell me it goes up because of interest. There is no interest. Interest is a joke. So, what we get from calcitonin is we simply stop the decrease in bone mass, and we stop the increase in blood calcium. So once again, just to be intentionally redundant, I need you to tie this in to so many other things. When we talked about cholesterol, and cholesterol forms steroids, and then we talked about estrogen and testosterone and how they stimulate the blast. And somebody whose body fat is too low, their cholesterol is too low, they won't have estrogen and testosterone, they won't be stimulating their blast. We have pathological fractures, we have stress fractures, thyroxine stimulating the osteoblast. We have so much that's come up in this world. It comes up again today in the context of homeostasis. Kind of just in conclusion, adding the hormones that act on the osteoclast specifically. For the sake of completeness, one of those things I wish I'd never said, like minimize what you have to memorize, but for the sake of completeness, if we continue broaden this topic, call it bone health. We have the hormones and the cells. And the whole homeostasis there. But what else do we have here? Talk about our diet. We need calcium in our diet. There's a vitamin that we need. D. Remember that word from Wednesday, absorption? And I said it means to move from the lumen of the small intestine into the vessel and the lamina propria. Without vitamin D, you can't absorb calcium. So you can eat all of the calcium you want to, but if you don't have vitamin D, you just pass your calcium. And then the third thing that we want to include here is exercise. Exercise stimulates your osteoblast. Now this is specifically weight-bearing exercise. It's not to diss swimming. Swimming is an excellent form of exercise. It exercises every muscle in your body, but it doesn't really do anything for your bones, is the thing. Swimming exercises every muscle in your body, cardiorespiratory, it's awesome, but for true bone stimulation, osteoblast stimulation, you need weight-bearing exercise. Okay, that takes us to the connective tissues. While I've got these documents pulled up, I'm sure you have, but I just want to make sure you have. In the, this is the document called Histology Supplement. I spoon feed to you right here what these different cells, different fibers do in connective tissue. In other words, if you look at only the notes, I list the fibers of connective tissue, I list the cells of connective tissue, but I don't tell you what they do. Well, so that you don't have to dig it out of the book, I actually tell you what they do right here. So you certainly want to, incorporate all of this into your histology books. As far as going through the connective tissues, try to follow along mentally. I'm sure most of you can, but insofar as the organization of connective tissue, because we don't have a strict nomenclature, do we? The way we do with epithelial tissues. But we do organize them a little bit. So we have the first group that we call either ordinary, or what else do we call that group? Saw it in somebody's notes in the lab last week. Connective tissue proper. Exactly, connective tissue proper. And the third thing we call this group is fibrous connective tissue. The problem with calling it fibrous connective tissue is they're all fibrous except which one of those is not fibrous? Adipose. Adipose isn't fibrous. But some people call that group the fibrous connective tissues and just make the point, oh, but adipose isn't fibrous. Connective tissue proper or ordinary, those are both fine things to call that group. Then we have the supporting containing bone and the three types of cartilage. And then we have the special, the very special, It's vascular connective tissue. It includes your blood, which is all we actually look at in this class. But, actual histology class, we look at the blood forming tissue as well, like the bone marrow and things like that. And you pick up some of that as you move through your various classes, including pathophysiology and medical surgical nursing, microbiology. Eventually you pick up most of it. I think the connective tissues are easier to recognize. You may not, I don't know. But I think they're easier to recognize just because it seems like they, with one or two exceptions, that they all look different from each other. I don't know, I just don't think that it's as easy to confuse any two of them. They're also very fast to go through. I don't know that, can't think of one right now. I might think of one before we're finished, but we don't really have to stop and draw on the board. They're pretty cut and dry to go through, and of course you got it right there in front of you. As I look around the room, I see it. So this, of course, is loose connective tissue. I guess a point to be made here, maybe I make it on the DVD, I'm not sure, but all of the fibrous connective tissues contain all three fibers. Okay, the fibers we talk about are the predominant fibers, the fibers that are easy to see. So if you just follow along mentally, flip through your books. When you think loose connective tissue, I know you think collagen and elastic fibers. Well, guess what? Reticular fibers are in there, you just don't see them. When you think dense regular and dense irregular, you think collagen fibers. Well, guess what? Reticular fibers and elastic fibers are in there too, you just don't see it. When you think reticular connective tissue, you think reticular fibers. Well, collagen fibers and elastic fibers are in there too, you just don't see them. So all three fibers are in every fibrous connective tissue. This, of course, is classic loose connective tissue. The source here, although it's probably not on the slide, but the source here is superficial fascia. That, of course, is the connective tissue that holds your skin to your muscle. If you've ever skinned an animal, I don't care if you hunt and you skinned a deer in the field, or if you're in the kitchen and you're taking the skin off a chicken breast. That white gooey material that's holding the skin to the muscle, that's what this is. There are a number of important cells in here discussed in the supplement. The mast cells, for example, making heparin and histamine. The plasma cells, what do they make? What do they produce? Those are the mast cells, heparin and histamine. Plasma cells. Antibodies, exactly. So there are a number of very important cells in here, but we can't really pick one out versus another. Okay? With something like this, I can say, name this cell, and you're going to say adipocyte. There's a couple of others where you can kind of play that game. Name this cell. Okay, come on, system. Oh, we can do it here. Name these cells. Chondrocytes. And then the last one where you can do that. What types of cells are in here? Osteoblasts or osteocytes. Now, speaking of this, we'll see who really pays attention to the DVD. First of all, what's this space called? Lacuna. Lacunae plural, lacuna singular. Just put an E at the end of the word to make it plural. What is in this space? Indian ink, or India ink. I didn't ask what used to be in the space. Bone cells used to be in there, osteoblasts or osteocytes. But what's in there now? India ink. That's on the DVD, right? That's very often a bonus question on the practical ability to see, who truly listens, transcribes, takes every single element of all of the materials I give you. So, there are certain tissues where we can play the game, name this cell, but there are others where we can't. I can't tell you if this is a plasma cell or a macrophage or a mast cell. I have no idea. I'm sure it's one of those three. What's the fourth possible cell for this? In other words, what type of cell makes these fibers? Fibroblasts. But I can't show you a fibroblast versus a mast cell versus a monocyte. I just can't do it. We could stain the tissue and make it possible to do that, but that has not been done. All right, we've got our two types of dense. Dense regular and dense irregular. The dense irregular takes us back to the skin, but we focus on the dermis of the skin this time to see the dense irregular. This, guys, just in case you don't know, this is what leather is made out of. When you want leather to make a belt or a pair of shoes, a billfold, you take the skin of an animal, cow, alligator, whatever you want. I guess you could use zebra skin. You'd probably go to jail. But you separate the epidermis from the dermis. You separate the dermis from the adipose, which is down here in the hypodermis. And then you prepare it with chemicals like glutaraldehyde, which is very similar to formaldehyde. It fixes, preserves the tissue. And there you have leather, and then you can use it to make whatever you want, billfolds, shoes, etc. That's what leather is. The other type of dense connective tissue, of course, is irregular. Regular. The dermis is the irregular. The other type is the regular. And the regular, the collagen fibers are in parallel lows. They're now, in this case, they're sort of wavy lines is the way they show up. If we took this and we stretched it, those wavy lines would straighten out. And it won't stretch very far because collagen is not very elastic. If you go back to your three types of fibers, the elastic fibers have two properties: elasticity and extensibility. Let's just check the documentation and make sure that I give you that. There you go, right there. Elasticity and extensibility. We take those two properties hand in hand as though they always go together, but they don't. To be extensible is to stretch, and to be elastic is to recoil. And almost everything we come in contact with as we're just, becoming teenagers, adults, whatever, we think about rubber bands. They stretch out and they return. Bow and arrow, slingshot, stretch it out, it returns. But they're separate properties. The ability to stretch is extensibility. The returning is elasticity. So these elastic fibers have those two properties. Something that is extensible but not elastic, except when you're in my kitchen, is pizza dough. You're supposed to be able to take that ball of dough and roll it out, and it gets thinner and bigger and fills the pan. How many of it do that? And you have to fight it, right? Because it recoils. You gotta stay! You want to almost scream at it. It's maddening. But it's supposed to be extensible but not elastic. It's just easier said than done. Anyway, so the collagen fibers, they don't stretch very much. They're strong. They're very, very strong. The document that I just closed out tells you they're stronger than steel. You take a collagen fiber and a steel fiber of the same diameter. A cool way to compare the elastic fibers and the collagen fibers would be, imagine that you take a climbing rope. Not a static rope for rappelling, but an actual climbing rope, which is dynamic. And you tie that rope to an immovable brick wall and a Jeep. And you let the Jeep take off slowly. That rope's going to stretch and stretch and stretch. It might elongate, 17, 20% before it snaps. Now do the same thing with a steel chain. Is that steel chain going to stretch? It's either not going to break, the Jeep's going to stop, or the chain's going to snap. It's not going to stretch. It's just going to break or be strong enough to hold the Jeep. Of course, the dense regular is found in your tendons and your ligaments. And they're not very stretchy. They either hold things together or they pop, bang. This is just another picture of dense regular. Another picture of dense regular. Put all of these in the slide set because it's a good example of not using color. I mean, you can, use color a little bit, but don't rely 100% on color to memorize your tissues. Right, the next type or another type of the fibrous connective tissues or the connective tissue proper is elastic connective tissue, so predominantly elastic fibers, but the collagen fibers and reticular fibers are there. This is actually a cross section through the aorta. So this is the lumen of the aorta. Now the aorta is the largest blood vessel in your body. It's an artery. It's bigger than your thumb. This is the lumen of the aorta. This is outside of the aorta. What type of tissue is that, by the way?
Adipose.
And you've got adipose everywhere. Some of you that next fall take my Biology 203, my advanced human dissection class, and actually do the dissection of the cadavers, you'll just plow through adipose. It's literally everywhere. But this tissue that's in between right here is the elastic connective tissue, and it's there because the aorta has to be able to expand and recoil. So if we zoom in, that's a little higher magnification, and now really high magnification. What we actually have here are sheets of elastic connective tissue, and the sheets are oriented so that you're looking at them like that. You're looking at this edge. And if they're tilted a little bit, you get an impression of thickness because you're seeing part of the top or part of the bottom. So the wall of the arteries, it's perforated with these sheets of elastic connective tissue. I don't know, I think this looks like Swiss cheese. And I remember that from a long time ago. Anybody remember when Luke and Laura got married on General Hospital? Most of you weren't born. School closed that day. That's how big it was. School closed. But yeah, we thought this looked like Swiss cheese, and we thought Highland cartilage looked like Smurf footprints, like Papa Smurf had stepped in Smurf berry Kool-Aid and walked out through the snow. And it's crazy the things I remember from the decades ago. But if it works, it works. This, of course, is reticular connective tissue. It's one that you can always use color to recognize. Several of you, a couple of you each day last week, and I have 4 labs, as you know, asked me what this is, and I told you it's called a venous sinusoid. You don't really have to know anything about it, but it's a little capsule, we could say, in the reticular connective tissue where blood is contained. And the cells that you see in there are primarily red blood cells because, as you know, most of the blood cells are red cells. I guess you maybe have to almost learn to look at it, but you're looking at the blood cells kind of like you're looking at the edge of the cell. So in other words, you're not looking at the cells like that. You're looking at the edge, more like this, almost as though you had a bunch of frisbees in there, and you're looking at the edges of the frisbees. Anyway, it's a helpful tool in terms of knowing, in addition to the color, to confirm what it is that you were looking at. Now, the reticular fibers versus the collagen, which are all about strength, elastic, which are all about flexibility, extensibility, elasticity. The reticular fibers are for internal structure. The reticular fibers are like the frame of a house. So you've all seen a house or a building being built. Imagine when you have nothing but 2x4s, 2x6s. If it's a big building, it's going to be I-beams, I suppose, not a lot of wood. But you just have the frame of the building, the frame of the house. Now you gotta come back and put the actual walls in, the ceiling material, the flooring. So that frame, that's what reticular fibers do to organs like lymph nodes, the spleen. Another analogy would be the cytoplasm of a cell, internal framework. This is, of course, adipose connective tissue, an example of where, hey, it's not difficult, it's just kind of picky. So name this tissue. Don't write down fat, write down adipose connective tissue. And if you want to use CT and ET, that's fine. You can use CT and ET throughout the practical examination. What do these cells store? Don't tell me they store fat, tell me they store triglycerides. It's kind of like, say, erythrocyte, leukocyte, thrombocyte, not RBC or red blood cell. We go back to the trachea to see the hyaline cartilage. It forms the rings to prevent the trachea from collapsing. Hyaline cartilage is, as you know, the most common type of cartilage in the body. We've got the cartilaginous rings in the trachea, the septum of the nose, the fetal skeleton, the ends of long bones, the costal cartilage. It is literally all over the place. Cartilage, just like with bone, you've got a fair amount of information on the supplement. In other words, you've got the lacunae with the chondrocytes in there, just some stuff that make sure you put it in your books and can use the words, spell the words, etc. This is another type of cartilage. This is elastic cartilage. One location of elastic cartilage is the external ear, as in this, and that's what this is exactly. And if you sort of look at it closely, I guess we can zoom in on a little bit. So this is skin. This is your epidermis up here. This is your dermis. You can tell this is dense irregular. You can tell this is keratinized stratified squamous. The superficial most aspect of the epidermis, the cells are actually flaking off. So we've got skin, and then in the middle, the elastic cartilage, and then on the other side, more skin. We can zoom in on the elastic cartilage and actually see that's what all these little black things are, the elastic fibers. We've got the chondrocytes and the lacunae. There's an interesting story that goes with this slide that has often been the bonus question on the practical. I've already told you this is an ear, and I actually made this particular slide. There's a little mouse that I used to see out in the parking lot, the west parking lot over here. I used to see him all the time, especially in the winter. When I would park, he would be sort of huddled up against the tires, because the tires are warm from the friction from driving. And I captured him one day, and I chopped off one of his ears, and I used the ear to make this slide, and I released him. He's still out there. You'll see him from time to time, especially in the winter when he's up against your tires trying to stay warm. If you see him, say hello. His name is One Ear. Okay, this is the third type of cartilage. It is typically blue. This is a sea of collagen fibers. This is fibrocartilage. This is all about withstanding compression. The menisci of your knees are made of fibrocartilage. Your intervertebral disc are made of fibrocartilage. Again, withstand compression. You can see chondrocytes in here. They're all the little pink, or whatever color you might say that is, but little pink dots. We get the magnification increased, and it becomes easier to see the chondrocytes. Then, of course, you have bone. Bone is a freebie. Looks kind of like trees that were cut down, and your mom or your dad talking to you about counting the rings to know how old the tree is. And I don't know if there's any truth to that or not, but while it's not difficult, there's a lot of verbiage that goes with this, and it's all spoon-fed to you on the DVD and in the supplement, so there's not really any need to rehash it in here, but in a nutshell, each one of these things, so that's one, there's another one, there's another one. In the last picture, there's one, there's one, there's one, there's one. What are those things? Haversian systems. The Haversian systems are divided into rings. What are the rings called? Lamella. There's a hole in the middle of the Haversian system called the Haversian canal. And in the lamella, we have these lacunae, which is where the osteoblasts were that form the bone. The bone is made from calcium. How do we get the calcium to the bone cells? Well, a vessel called a Haversian vessel runs through the Haversian canal, but the blood has to perfuse from the vessel out to the osteoblast. So there are little microscopic channels that we can see here in each Haversian system, and those little microscopic channels are how the blood perfuses out to the osteoblast. What are those little microscopic channels called?
Caniculi.
Caniculi. So again, it's not difficult, and it's all given to you in the supplement on the DVD. Just make sure you have it. And finally, for our blood section, again, we just look at blood. We don't do hardly anything with it. So this is blood connective tissue. Make sure you know all of those numbers. So what do we have here? We've got 45% cells, 55% water, or 55% plasma. The plasma is 91.5% water, 7% protein, 1.5% other. The cells are, 94% red, 6% thrombocytes, 0.14% platelets. Next semester, we add to all of that, we take the white blood cells, neutrophils, basophils, eosinophils, monocytes, lymphocytes, get their percentages. Then we take the lymphocytes, divide them into T cells and B cells. Where are they made? T cells, T helper cells. We talk about the HIV virus. And so we add a lot to this next semester. Do realize, because it's interesting, I suppose, red blood cells are anucleated. They don't have a nucleus. Sometimes we think we see the nucleus in red blood cells.
No, they're just thin spots.
Huh?
They're thin spots.
They're just thin spots. Perfect, exactly. They are just thin spots. Let's This is a picture from a scanning electron microscope. I pointed out last week that electron microscopes, you have two types, transmission and scanning. The scanning takes 3D pictures. This is magnified 1,838 times life. Really cool picture. But look at those red blood cells. You see how the center is thin. So if you were to look at this from the side, they look like that. From the top or the bottom, they look like that. And so this thing in the middle is not a nucleus, it's just where the cells are thin. They lose their nucleus as they are maturing. And you'll recognize this from the DVD as well. In reticular connective tissue, the cells that make the fibers are called reticuloblast or reticulocytes. Some people have trouble with those words because a reticulocyte is also an immature red blood cell. So anyway, they show here the nucleus being ejected as we move to the actual mature red blood cells. So red blood cells are anucleated. Okay, so I'm going to sort of quiz you. Before I do, I want to just just because I'm old and I forget things. So last week, it seems like we had a little 5 or 10 minutes at the end of some class, and I did point this out, right, to review all of these rules about testing. Okay, so this is big, guys, okay? Your exam is Wednesday. You've got to know this. There are questions on the exam from the syllabus, okay? So you need to be familiar with the syllabus, but you specifically need to be familiar with the rules for testing. I always thought it went without saying, but you have to use the number 2 pencil on a Scantron. I had a couple of people in more than 25 years try to use a black pen on a Scantron. It gives the computer indigestion, okay? You have to use a number 2 pencil on a Scantron. It's the only thing that will work. But again, read all of this very, very carefully. The exams are timed. My exams are typically 90 questions. So that's a lot of questions. You'll have an hour and 20 minutes to do it. You want to keep up with your own time. When I say go, you look at your watch. Because see, a class may start at 8:30, but when I say go, it won't be 8:30. And everybody's watch is different anyway. The only way you get the exact time is to look at your phone. Well, I guess there are watches that give the exact time. But when I say go, you look at your watch, you write down what it says, and then you add 1 hour and 20 minutes. And so now you know at 10:57, I'm going to say put your pencils down, okay? Rules in here talk about what if you don't put your pencil down? What happens? What if you answer all of the questions in the examination booklet, but you don't get the Scantron filled out? What happens? So again, read all of this stuff. Know what it says. Be prepared. Now, most people finish exams in well under the allotted time, so you don't need to really worry about it. Sometimes when we're testing, so now I'm going to quiz you. Sometimes when we're testing in the lab, I get so tired of making up questions that I'll let you guys do it. So we'll do that. Somebody pick a number. 91. Actually, let's make it more challenging. All right, pick a number. We can still do 91, but you've got a lot
42.
more numbers now. Huh? What?
42.
42.
Where'd you say it's at?
42. All right, do you want to use this, or do you regret picking 42?
Well, it's just a different number.
Choose a different number? Okay, somebody else pick a number. I'll pick 74. All right. First person that asks a question I like, that is the question. Don't all speak at once.
What's the main type of fiber there?
What's the main type? Now that's going to be plural in this case.
Fibers.
So what are the 2 predominant fibers found here? Collagen fibers and elastic fibers. So we really do that in the lab, okay? We really do that. They're not all like that, but some of them. Somebody pick a number.
67.
97. First question I hear that I like, that becomes the question. And if you need me to increase the magnification, because I mean everybody knows it's the trachea, and if you're wanting to ask about, I don't know, the 3 types of cells found in PSCCE, maybe you want more magnification. So you might say, I like what I picked, but could you increase the magnification and zoom in on the, don't say PSCCE, but zoom in on the lining? And I'll say, yeah, we can do that. Make sure I'm doing what you want. That's not it if I understood you correctly. That's not it if I understood you correctly. Oh, we're going to have to go somewhere else. In other words, we must have been in the connective tissue section, and we need to be in the epithelial section, and I don't have any thumbnails, so I can't really continue. But, all right, I'll pick one. What type of gas moves from these structures into the atmosphere? CO2. Very good. Give me a location of this tissue other than the location that you're looking at?
Kidney tube.
Okay, let's not say kidney, let's be more specific. Bowman's capsule, give me another one. In the kidney, give me a second one in the kidney. Glomerulus. Give me one that's not in the kidneys. Capillaries. Give me 2 locations of this tissue and their respective functions.
Tendons and ligaments.
Tendons and ligaments, okay. Now somebody else, what's the function of a tendon? What's the function of a ligament?
Tendon is bone to muscle.
Tendon connects muscle to bone.
And ligaments connects bone to bone.
Ligaments connect bone to bone. Exactly. So examples of ligaments, just to give you something you can relate to. We take a look at your knee. It's an anterior view of the knee. We've got the proximal femur, the distal tibia and fibula. So you've got 4 major ligaments in here, the ACL, the PCL, everybody's heard of those, the tibial and fibular collateral ligaments. So they're holding one bone to another. And if your bones are supposed to be held at a certain orientation and you get hit back here and your tibia goes, whoa! Well, something tears, right? Something tears. So, we were looking at, what type of tissue was that we were looking at when I asked about the fibers? Was it loose connective tissue?
The one that he asked about the question.
Well, let's see. We were looking at this. Weren't we looking at this? I asked about the 2 locations. And you said what? Tendons and ligaments. Then we got into the functions, and then I tried to show you a picture, a macroscopic picture of some ligaments just for perspective. And so now we're back to name the tissue. Dense regular. What type of cell produces the predominant fibers in the tissue?
Collagen fibers.
What type of cell produces them?
Oh, sorry.
What? Fibroblast, yes. $50 to the young lady on the 3rd row. All right, well, we're about out of time. I'm sort of tired of this. You guys seem to be tired of it too. So I'll see you in the lab.